Alright, so today it's day 71. I solved 3 more LeetCode problems. Let's go ahead and solve them again. Let's go quick. So the first one is this one, lowest common ancestor in binary search tree. So we know that the main property of BST, binary search tree, is that the left child is going to be smaller than the root, and then the right child is going to be greater than the root. And we gotta return the lowest common ancestor. And okay, I'm gonna just go ahead and quickly show. So the lowest common ancestor of a node is gonna be, we have, I don't know, if we're given these two nodes, the lowest common ancestor of every node is always the root. But if we are given, I don't know, these two, this is gonna be the lowest common ancestor. The second property is that the lowest common ancestor of a node is always itself, right? But we know that the root is common ancestor to every node. We just want that's why we want the lowest one. So if we have these two, we have this ancestor and this one, but the smallest one is the 3, so we gotta return that. So in order to solve this, the only thing that we do is essentially iterate as if it was a linked list. And for example, if we're given the 3 and the 4, we start at 5, and here we check both of the values that we want to check are smaller than 5. It means that they are to the left, because we know how it works, BST. So I can just remove these and ask the same for this one. In this case, both of the values are neither to the right nor to the left. So we're gonna return the current node. That's it. So that's it. We check if they are either to the left or to the right. If they are to the left, we move left. If that's not the case, it could be that we have something like this. In its case, this is gonna be the lowest common ancestor, or we have something like this, in which case it's also the same. So we can go ahead and implement it. So it's gonna be, I mean, it's very similar to linked list. So it's while current, we gotta ask ourselves the condition, which in this case is p.val is less than cur.val, and q.val is less than cur.val. If this is the case, we need to move it to the left. So I gotta say cur equal to cur.left. If not, we're gonna check. We also have to check if they are greater. If this is the case, we know this is to the right. And if this is not the case, we can stop early and return the current. And if this is not the case, it means that they're giving us like an empty. So we finish this one. Let's go ahead and solve the next one, binary tree order traversal. So this one is essentially implementing BFS, breadth first search. The only caveat is that we need to keep track of the levels. So this would be the output with BFS, but we want to at each level group as a list. So that's it. So we know that to implement BFS, we can use a queue. We pass at the beginning the root, and while DQ. And here is the interesting part, because how do we keep track of the levels? And the answer is pretty simple. You simply count, like put a for loop inside the while that keeps track of the length of the queue. Because in this way, like if you add the 1, the first level has, like the length of the queue is gonna be 1, so the level has 1. Then you add 2 and 3 to the queue. Then you compute the length, so you're gonna have 2 and 3. And then for every value in the queue, so you have 2, and then for the 3, you're gonna add 2 values. So you're gonna have 2 values here, and for the 3, you're gonna have 2 values. So then for the next iteration, the length of the queue is gonna be 4. So I mean, that's it. So in range length of the queue, and we need to keep track with a list at each level. We also gonna return the rest. So now we can check if the way how BFS work is we check if the node to the left exists. So I can say if, okay, first I gotta pop it. So I'm gonna say node equal to the queue.pop from left, and we can append this value to level. So I'm gonna say level dot yes is append. We gotta append yeah, we need to return the value. So I'm gonna append node.var, and if node.left is not empty, so it's not none, we're gonna move. We're gonna append this to dq. So I'm gonna dq append node.left, and this is the same for node.right, dq.append node.right, and we need to res.append it to the result each level every time this finishes, and we gotta return res. So here the thing is that they are giving us as an input an empty, so if not the root, we can return directly this one. Okay, so we solved this one. Let's solve the last one very quick. So we're given a binary search tree, and we are given a tree, and we have to say if it's an actual binary search tree. The way to do it is just to perform BFS and check like the main condition of BST, which I set already that it's just checking if the node is less than the predecessor, if it's in the right side, if it's in the left side, and if it's in the right side, if it's greater than the predecessor. So I'm gonna create a helper function. I'm gonna call it DSF, and we're gonna pass the root and 2 parameters, because these are gonna be, this is like a trick to do this, because in the end we're gonna call this function DSF over root, and essentially if we pass this to a left node, like we're at 2 and we pass this to at 1, we want this left to be always true, right? So I can pass a condition that I know it was always true, which is like if it's less than infinity, so this is gonna be true. So I can check just directly minus float of infinity. The thing is, like, everything kind of starts to make more sense when you have like the whole solution all together. If not node, if not root, we're gonna return none. No, we're gonna return true, because if the edge case is that you're at the end, you check both children. If both are none, you do it for the left, you have a value which is gonna be true. Then you do it for the right, you have also true. Both are true, then you return, because the returning condition, we know that to apply DFS is going to be DFS of something, and here DFS of something. So in order to be valid, a binary search tree, it has to be valid for both the children nodes, right? So I'm going to say now we check the actual condition that we want, which is going to be left equal to root.val less than high, and if this is true, it's valid, but we need to check if every node is valid. So we can say if it's not true, then we stop early and we just return false. And now we can, if it's valid, we need to go to children. So first we do the left one. So we pass low, and the left children, which is in this case the one, has to be less than the parent, which is going to be just root.val, right? And root.right, root.val, right. Okay, we have an error. I'm not making any. They have to return something. Yeah, obviously, right? But still there's an issue. What is this? DFS. Okay. Name R is not defined because I'm using high. Okay, good. So this is it for today. I'm gonna start doing like all the problems more quickly, because I think there are better videos in YouTube explaining like the problem. So yeah, that's it.